let's have a look here at this 2004 one. It says that the experimental diving bell shown above is lowered from rest at the ocean surface and reaches a maximum depth of 80 meters. During the descent, the pressure inside the bell remains at a constant 1 atmosphere. The top of the bell has a cross-sectional area of 9 square meters, so that's the entire top there. The density of seawater is 1,025 kilograms per cubic meter. So first thing they want you to do is to calculate the weight of the water on top of the bell when it's at its maximum depth. So remember that weight is going to be the force of gravity, which is going to be mass times gravity there. Whoops, sorry. Let me move that over. And then we got to do our substitution for mass, and so that will be density times volume times gravity there. So now let's substitute in for volume. We can imagine, right, that there is this column of water above it that has a base of 9 square meters, but a height we're 80 meters deep. So we're going to replace volume with area times height. And so finally we've got all the substitutions in there. We can put everything in. Whoops. The density is 1,025. They got to go and make it difficult and make it seawater there. So 1,025 kilograms per cubic meter. The area is 9 square meters. The height is 80 meters. And gravity, let's just round it off to 10 meters per second squared. And if you multiply all that out, you will get 7,380,000 newtons is the weight of that water. Whoops, and sorry, I crossed a little bit out there as well. I'll have to watch that, keep it all on the screen. B says calculate the pressure on top of the bell at maximum depth. The absolute pressure on top of the bell. So the absolute pressure will be atmospheric pressure plus density times gravity times height. So that equation is on your equation sheet there. We can just substitute in for all of these straight away. So atmospheric pressure is 100,000 pascals. The density again is 1,025 kilograms per cubic meter. Gravity is 10. And the height, so to speak, the depth is 80 meters. So when you multiply all of those out, you'll get 820,000 for this one, plus another 100,000. So about 920,000 pascals, or 920 kilopascals, they might report it as well. On top of the bell, there's a circular hatch of radius r equals 0.25 meters. So here's the little circular hatch right there. Calculate the minimum force necessary to lift open the hatch of the bell at maximum depth. Well, you might start to think that you've got this pressure on top of you here, and you need a force to overcome that pressure outside the bell. So if I rearrange this equation, the force I'm going to have to exert is going to have to be equal to the pressure on top of that hatch times the area of the hatch there. So the pressure, once again, we're going to use our equation that pressure is density times gravity times height, and then we'll multiply by the area there. Remember the area, be careful here. There's a tendency on this problem to use the 9 square meters, but that's the area of the entire surface of the bell, not the hatch. So to get the area of the hatch, we got to do density times gravity times height and substitute in for the area pi r squared to get the area of the circular hatch there. So let's plug in all of our numbers here. Once again, density is 1,025 kilograms per cubic meter. Gravity is 10 meters per second squared. Height is 80 meters. Pi there, and then the radius is 0.25. Don't forget to square it. And you should, in that case, get 161,000 newtons as your answer there. Last part here, what could you do to reduce the force necessary to open the hatch at this depth? Justify your answer. The most common answer they look for is increase the pressure inside. Right? Because the more pressure you have inside, the less the difference is in here. So we have some pressure inside, which is 1 atmosphere, and we have the pressure outside. So inside we know it's an atmosphere, so it's 100,000 pascals. And outside we figured it's 920,000 pascals. absolute. So it's an 820,000 difference there. And so in order to reduce that difference, it would make sense to increase the pressure inside.